Okay, the Earth also generates heat through decay of radioactive isotopes like uranium and thorium. So both decay at a rate that is, it's not 1 million years, it's 10,000-ish. Every 10,000 years, half of that fuel disappears. Every 10,000 years, you got half as much, half as much, half as much, half as much. So you can imagine how much you had to have when the Earth was created till now. Somebody should do that calculation, figure out how many times 10,000 goes into 10 million, or 1 billion. Yeah, how many times does 10,000 go into 1 billion? And then figure out how much radioactive material is left, because it ain't fucking much. Anyway, this process contributes to the overall heat of the Earth's interior. So there's just absolutely zero evidence that this radioactive decay theory has anything to do with reality. They just have zero evidence. No reason to believe it. And it's on its face idiotic, frankly.
So, our genius has spoken again, people. This person claims to be the next Einstein, but in reality, he's just an uneducated moron who once again makes up a fable. In this case about the half-lives of radioactive isotopes, as always, you're wrong, Gary. He's claiming uranium and thorium isotopes decay very quickly, half-life approximately 10,000 years. Therefore, almost all of them would be gone after billions of years. Hence, radioactive decay cannot possibly be contributing heat today. So the radioactive decay theory is supposedly false. That sounds logical if his assumption about decay times were true, but it's completely wrong about the half-lives of these isotopes. These are the actual half-lives. So these isotopes decay millions to billions of times slower than Gary suggests. If their half-lives were only 10,000 years, they'd have vanished completely long before life even began, and Earth would be stone cold. Now, how can we know what the half-lives are of these isotopes? Well, scientists have measured it. Let's unpack how we actually know the half-lives of uranium, thorium, potassium-40, and other radioactive isotopes. 1. We measure decay directly in the lab. Radioactive decay is a statistical process. Every atom has a certain probability per second of decaying. We can count those decays very precisely with modern instruments. How it's done. Take a pure sample of the isotope, for example, uranium-238. Measure how many decay events per second, disintegrations, occur. This is the activity in becquerels. Knowing how many atoms are in the sample, you can calculate the decay constant lambda. The half-life is then given by, even though uranium decays slowly, its activity is measurable because there are huge numbers of atoms in any macroscopic sample. 2. We can also check by watching decay chains. Many isotopes, like uranium-238 and thorium-232, don't decay in one step. They go through a chain of shorter-lived daughter isotopes. By measuring the ratio of parent to daughter isotopes and the activity decay rate of each step, we can confirm that the half-life of the parent is consistent with the measured ratios. This method has been repeated for more than a century, every time with the same results. 3. We can see radioactive decay over geological timescales. There's a second independent check using radiometric dating. When minerals form, they trap certain isotopes like U and Pb. Over billions of years, uranium decays into lead at a predictable rate. By measuring the ratio of uranium to lead in ancient rocks or meteorites, we can confirm that the decay constant used matches the observed ratios. Cross-check with other decay systems, e.g. Rb-SR-K-AR. These independent methods give identical ages, confirming that our measured half-lives are accurate even over deep time. 4. Consistency across multiple methods. The same half-lives are confirmed by direct lab counting, shorter-lived isotopes, counting daughter products, longer-lived isotopes, mass spectrometry of natural samples, nuclear theory, quantum tunneling models predict very similar rates. 5. Key point, it's not assumed, it's measured, cross-checked, and observed everywhere. We know the half-lives of isotopes the same way we know the charge of the electron or the speed of light, through repeatable, precise measurements that match observations in nature. Even if all Earth-based labs vanished tomorrow, we could still confirm the same decay rates by looking at isotopes in meteorites, the moon, and cosmic rays, all showing the same decay behavior. In summary, we know the half-lives of uranium, thorium, and other isotopes because we can directly measure their decay rates, confirm the results through isotope ratios in rocks, and predict them theoretically from nuclear physics. Every independent line of evidence gives the same numbers, over time scales from seconds to billions of years. So stop lying, Gary. Stop making things up. Do your research and get your lazy ass.